Hello, myself Shubhashish Shah, Assistant Professor of Mathematics of Greater Kolkata College of Engineering and Management, GIS Group. In this video, I will discuss about how to find the particular integral to solve a higher order first degree linear ordinary differential equation with constant coefficients. In the previous video, I discussed about how to find the complementary function, and we know that the solution of this type of equation contains two parts. One is CF, another is PI, complementary function and particular integral. In the previous video we have learned how to find out CF or complementary function. Now in this video we will discuss about how to find particular integral, that is PI. Now, first I have to say some basic things. I am writing the general form again. D square y dx square plus p1 dy dx plus p2y equal to capital X, where p1 p2 are arbitrary constant and capital X is a function of X. I told this. And we can write this equation using capital D, where capital D is the differential operator. D square plus P1D plus P2 operating on Y is equal to capital X. Now, this operator is on the left hand side, and with the help of this operator we found the complementary function. Now we are transferring this operator from left hand side to right hand side. If we transfer this will be like y equal to 1 by d square plus p1d plus p2 operating on capital X. So this will help us to find out py or particular integral. So how to calculate or how to find out particular integral from this type of function? Okay, so before starting discussion on this, I will tell you two theorems, and this is needed to know. So first theorem is we know that capital D is the differential operator. So 1 by D is also an operator, and 1 by D operating on some function capital X means it is integrating capital X. Okay, so 1 by D is the integral operator, that is reverse of capital D, reverse of differentiation. So how it works? I'll prove this. I'm assuming that y equal to 1 by D capital X. Okay, now I am operating by capital D both sides, that is I am simply differentiating. So this will be dy will be d 1 by dx. D is operating on the both sides. Okay, now we know that capital D is a differential operator here with respect to x. So this will be dy dx, and this will be x, because differentiation and integration are working both simultaneously. So if dy dx is equal to capital X, then y will be integration of capital X dx. Therefore 1 by d of capital X is equal to integration of capital X dx. So this is the proof. So this is very important for solving PI. As you know, D is the differential operator, so 1 by D is the integral operator. Okay, now the next theorem I am doing here, theorem 2. 1 by D minus A capital X, 1 by D minus A capital X is equal to e to the power ax integration capital X e to the power minus ax dx. So I'll prove this now. 1 by d minus a capital X, I am assuming this is equal to y. Let y equal to 1 by d minus a operating on capital X. Now we are operating by d minus a both sides. We are operating by d minus a on the both sides. D minus a, 1 by d minus a operating on capital X. Now d of y means dy dx minus ay equal to, this will be capital X because they are reverse function and working simultaneously. So this will be dy dx minus ay equal to capital X. Now you know that this is a first order first degree equation and a linear type equation, which in my previous video I have discussed how to solve a linear first order first degree equation. So the integrating factor will be e to the power integration minus a dx, that will be e to the power minus ax. Now we multiply this equation by this integrating factor. So multiplying by integrating factor, we will get d dx of y into e to the power minus ax, that is integrating factor, is equal to e to the power minus ax into capital X. Okay. Now I am writing in this side because in that side light is reflecting on the board. So in the next step I am integrating both sides. Integrating both sides, we get y into e to the power minus ax equal to integration e to the power minus ax capital X dx. So y will be equal to e to the power ax into e to the power minus ax capital X dx, and y is our required 1 by d minus a capital X, and that is equal to this. So the theorem is proved. Now these two theorems are very important to find out pi. So this second theorem is more important because I told you that this function will help us to find out pi, and the theorem number 2 is very important because we have to apply this theorem number 2 to find pi if we follow the general procedure. There is many procedure. The general procedure is this theorem number 2. What to do? This function have to be factorized. Since this is a quadratic function and we are considering all second order, if second order ODE, if this is third order ODE or more than that, then this function will be the degree of this polynomial will be equal to the order of the ODE. So this is not the factor. The factor is we have to factorize this operator, this function. So after factorizing we know that this type of functions are factorized into two factors because the degree is 2. If the number of factors will be equal to the degree. So suppose after factorizing, this is the result, 1 by d minus a into 1 by d minus b operating on capital X. Okay. Now we have to split this function in partial fractions. So after splitting in partial fractions, this would be m by, no, I will not use m, suppose c by d minus a and plus e by d minus b operating on capital X. And if we split it, c by d minus a operating on x plus E by D minus B operating on X. So now see that this, if we want to solve this type of function working on X, operator working on X, we have to apply theorem number 2. This is of the same form. So theorem number 2 is very important if we want to follow the general procedure. Okay. But this general procedure is very lengthy. I am again repeating briefly the procedure, general procedure. This denominator, that is function of D, have to be factorized. There will be 2 factors. Then we have to split it in partial fractions. And after splitting it into partial fractions, you will see that theorem number 2 can be applied on those functions. Okay. Then it will help us to, the result will be the particular integral. But this general procedure is very lengthy. So we use some another procedure. There are some another procedures. We use those procedures and they are quite short in length. Okay. So I will discuss about the short procedures now. Okay. So there are some different cases for different functions. In the right hand side function, there is capital X in general form. So I am writing capital X for general form. For all the methods I will show you. Okay. So case 1, if capital X, Pi is completely dependent on the right hand side function capital X. And now I will consider various types of function. Okay. So if capital X is e to the power ax, that is exponential function, then what will be the Pi? Okay. First I should write here. Pi is 1 by d square plus p1d plus p2 operating on capital X. This is the Pi. Okay. The D operator, the operator, that is function of D, has been transferred from left hand side to right hand side, and this is the Pi. Now case 1, if capital X is an exponential function, that is e to the power x, then we put D equal to A. Just we put D equal to A. So the Pi will be 1 by, I am writing this function of D. So after putting D equal to A, this will be 1 by Fa operating on, sorry, operating, not operating, it is constant, 1 by Fa into X. And this is the Pi. This is very short procedure. Okay. Just put D equal to A if the function is an exponential function. A is the coefficient of X. I am showing an example. Suppose 1 by D square plus 2D plus 1 e to the power 3x. So since this is an exponential function, we will put D equal to 3. Here A equal to 3, coefficient of X. So 1 by 3 square plus 6 plus 1 e to the power 3x, that is 1 by 16 e to the power 3x. This is the particular integral. Okay. So it may be happen that if we put D equal to A, after putting D equal to A, the denominator becomes 0. Then it will be undefined. So in that case, D equal to A. Now I am discussing subcase number A. This is under case 1. That is after putting D equal to A, if Fa equal to 0, then Pi will be, actual Pi is 1 by Fd operating on X, and we put D equal to A, we see that Fa equal to 0, then the Pi will be X into 1 by F dash D operating on capital X. Just we write an x and we differentiate the function of d once, and this will operate on x. Sorry, this is not x, we are considering e to the power, we are working with e to the power x, and again put d equal to a. Again put d equal to a. So the pi will be x into 1 by f dash a e to the power ax. Okay. So also it may happen that after putting a in place of f dash d, in place of d in f dash d, it can be again 0. F dash a may be 0. So same procedure will be followed. If this is also 0, if f dash a is also 0, then same procedure, there will be another x, that will be x square, f double dash d, again differentiate e to the power ax, again put d equal to a. And this procedure will go on till the value, after putting d equal to a, the value of f, nth order differentiation of fd is non-zero. Okay, so I am giving two examples for two cases, if f dash a equal to 0, if f double dash a equal to 0. Okay, one by d square plus 5d plus 6 e to the power minus 2x. Now see that since this is an exponential function, we know that we have to put d equal to a. Now if you put d equal to minus 2, then you see that this will be 0. So since this is 0, we have to write here x, and we have to differentiate this function once, 2d plus 5 e to the power minus 2x. Now again put d equal to a. Now here if you put d equal to minus 2, this will be minus 4 plus 5, that is 1. So e to the power minus 2x. So this is the pi. Okay. Since first after putting d equal to a, this was 0, so we follow this procedure. Now another example, 1 by d square plus 4d plus 4 e to the power minus 2x. Now here you see, if you put d equal to minus 2, then it will be 0. So we have to write an x, differentiate once, that is 2d plus 4 operating on e to the power minus 2x. Now again put d equal to minus 2. Again you see that this will be 0. That is f dash minus 2 is 0. So again we have to write another x, that will be x square. Again we have to differentiate, we are repeating the procedure just. If we differentiate this function, this will be 2 e to the power minus 2x. Now since there is no d, we will not have to put d equal to a. So this is our pi. So our target is to eliminate d from the denominator. So x square by 2 e to the power minus 2x. This is the pi. Okay, so I just discussed about if the function, right hand side function is exponential function, then how to find pi. Okay. Now I discuss another function. Now another function, second function, if capital X is sine or cos function, then in the pi we put d square equal to minus of a square, that is pi is 1 by fd operating on capital X, put d square equal to minus a square. Do not put anything in place of d, put minus a square in place of d square. Okay. Now I will give an example. Suppose there is 1 by d square plus 9 sine 2x. So here a is 2, that is coefficient of x. Okay, so put d square equal to minus 2 square plus 9 sine 2x. That is 1 by minus 4 plus 9, that is 1 by 5 sine 2x. So simple, if there is sine or cos function, put d square equal to minus a square. Now, like exponential function, it may happen that after putting d square equal to minus a square, the denominator it becomes 0. Then we have to follow the same procedure we followed in the case of exponential function. Though I am giving an example. Suppose there is 1 by d square plus 9 sine 3x. Then you see that if you put d square equal to minus 9, then the denominator is 0. So, like exponential function, we are following the same procedure. We are writing x and differentiate once 2d operating on sine 3x. Now x by 2 and here 1 by d. And in the starting of this video, I have proved that 1 by d is equivalent to integration. That is integration of sine 3x. So this will be minus cos 3x by 3. That is minus x by 6 cos 3x. So if after putting d square equal to minus a square, if the denominator is 0, then we will follow the same procedure as in exponential function. Okay. Now we are giving another example. Since there is 1 by d square plus d plus 1 sine 3x. If there is any d, then what will we do with that d? We have put d square is minus a square in place of d square, but I have not told you that what to do with only d, with which power 1, power of which is 1. So if we put d square equal to minus 9 plus d plus 1 sine 3x, and this will be 1 by d minus 8 sine 3x. Now you can't put d equal to a, this is only for d equal to a is the rule only for exponential function. In case of sine cos function, you have to put d square equal to minus a square, do not put anything in place of d. So we'll just multiply by d plus 8 in the numerator and denominator, so that in the denominator d square comes. So if we put d plus 8, if we multiply, then this will be d square minus 64 sine 3x. Now you can put d square equal to minus 9 again. So we are putting d square equal to minus 9. This will be minus 73 d plus 8 sine 3x. Now minus 1 by 73. Now d plus 8 of sine 3x operating on sine 3x. So if d is operating on sine 3x, what is the function of d? Differentiation. So differentiation of sine 3x will be 3 cos 3x plus, and 8, since 8 is a constant, it will just multiply sine 3x. So it will be 8 sine 3x. Okay, so this is the particular integral. If the right hand side function is a polynomial function, so particular integral, we know that looks like this, 1 by fd operating on some capital X. Now if capital X is a polynomial function, in this case I am directly taking an example. 1 by d square plus 2d plus 3 operating on x square plus 5x plus 6. Now x square plus 5x plus 6 is a polynomial function. So in the first step, we have to take the denominator in a certain form. The forms are either it will be 1 plus x to the power minus 1, or it will be 1 minus x to the power minus 1. So we have to bring 1 in the denominator in a term. Okay, so we can take common any one, but we will always take common the term with least power of d. Here the least power of d is in this term, that is d, the power is 0, so we will take common 3 if there is no 1. If there is 1, then we will not require to do this all. So since there is no 1, we are taking common 3 to bring 1. So this will be 1 plus d square plus 2d by 3 x square plus 5x plus 6. Now this is 1 by 3 into 1 plus d square plus 2d by 3 to the power minus 1 operating on x square plus 5x plus 6. Okay. Now this is the form identical with this form 1 plus x to the power minus 1. Now I am writing on this side 1 plus x to the power minus 1. The formula of this is 1 minus x plus x square minus dot dot dot. This is an infinite series, and the formula of 1 minus x to the power minus 1 is 1 plus x square plus dot dot dot. Okay. So here there is 1 plus x to the power minus 1 in this form. So I will apply this formula 1 by 3 into 1 minus d square plus 2d by 3 plus d square plus 2d by 3 whole square minus dot 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 operating on x square plus 5x plus 6. Now the question is, till how many terms we will have to write here? Okay, since there is an infinite series, this will depends on this polynomial function. Now you will understand how it happens. See, this is the operator which is operating on x square plus 5x plus 6, and all the d's are in the numerator. So these all d's will differentiate this function. So this function can be differentiated if we differentiate once this function, then it will be 2x plus 5. If we differentiate twice this function, that will be 2, and if we differentiate thrice, then it will be 0. If we differentiate thrice or more, this will be 0. So you see that in this expansion, here d square, there is d, and in this term there will be a d square if we expand this, and in all the remaining term the power of d will be greater than 2, and the result of those operator operating on this function will all be 0. So you will have to first see this function and till how many number the function can be differentiated, and on that it will be dependent that till how many terms you will write this infinite series. Okay, so now I will operate this. 1 is operating on this means multiplication, so x square plus 5x minus plus 6 minus d square of this term, that is double differentiation of this function, that will be 2 by 3 minus plus minus, I am splitting directly, 2 by 3 into d of this function. D of this function means 2x plus 5, first order differentiation, plus d to the power 4, that will be 0, 4d cube, that will be 0, and the last term will be 4d square by 9, that is 4 by 9 into double differentiation of this function, that will be 2. So the result is 1 by 3 into x square plus 5x plus 6 minus 2 by 3 minus 2 by 3 into 2x plus 5 plus 8 by 9. So this is the particular integral. If the right hand side function is a polynomial, you have to apply this procedure. Okay, now you practice this type of sums. If you face any problem during practicing, you can contact with me. My contact details is given the first of the video. Thank you.